This material is made available to you by or on behalf of the University of Melbourne under Section 113P of the Copyright Act 1968. It may be subject to copyright. For more information, visit the University Copyright website.
Hi everybody, good afternoon, and welcome to our 7th week of algorithms for functional genomics. Just before we get to the actual lecture, I just have a very important announcement to make that reflects on our lectures and is the following. So, by a mistake, our lecture originally booked for the 27th of September will need to be replaced because the 27th is a university holiday. So it's a Friday and we'll have a lecture and 2 tutorials. And because of that, unfortunately, we'll need to arrange a replacement. I've just managed to do that. So that lecture will move to the following week, the Tuesday, on the 30th. And that will be from 1 to 2 p.m. at Chemical Engineering 1 Building, room G20. And the 2 tutorials will be on the same date, early in the morning, from 10 to 11. Then another tutorial from 11 to 12 at the Electrical and Electronic Engineering Building, room 121. I'm really sorry for this. There's not much we can do about it. Yes? The 27th is just before it, I think.
Yes, so the actual lecture is during the semester, right?
This one? Is it? Okay, we need to change it again then. Not a problem, we change it again. It couldn't be on the 27th. If that's the break, will be the following week then. But just before, which day would that be then? 6th of October or something like that. So forget about this. I was about to post this on LMS. Good thing I didn't. Thank you very much. Yeah, that was actually booked. So I don't know how they managed to book this again. So I scraped that one. And then I'll post it on LMS once I have actual valid dates. Okay? Sounds good? Sorry about the confusion. This really shouldn't happen. And yeah, today we're going to change topics a little bit. So I'm sure you all enjoyed hearing from Simon, extremely experienced, very, very nice guy, and I think we learned quite a few things about him. Today it's back to me, and we'll change topics a little bit, but not a completely new topic. We'll talk about graph theory this week. And we've been talking about graphs since week 2 or 3, when we talked about phylogenetic trees. Trees are a specific type of graph, and last week Simon also covered the Brown graphs, which are extremely important as well. And this week we'll talk a little bit about graph theory in general. And just for you guys to have an overview of what is to come, we'll talk a little bit about graph applications in general, just for some motivation. We'll introduce a few important concepts in graph theory and a few interesting algorithms. Mostly, we'll talk about data structures, how do we represent graphs and networks in a computer, and we'll focus on 2 important algorithms that are related to graph traversal. So how do we visit vertices in a graph in a systematic way? And on Friday, we're going to talk about network analysis and network characterization. So how do we extract information from complex networks and the different graph models we have? So if we have a new modeling, let's say you have data that you believe it's interesting to model as graphs, how do you extract information from it, whether it fits in any known graph model? For instance, if you have a random network, that might be due to an issue with your modeling, maybe something wrong there, but there are also classical graph models. For instance, I'm sure everybody heard of small world networks and 6 degrees of separation and all that, and how that impacts our network and the information we can extract from it. So today we're going to start with basic concepts and a few interesting algorithms. So just as an overview, so graphs, they model objects and their interactions. And biology is full of interactions. So if we think about it, just the things we've seen during this semester, for instance, phylogenetic trees. So we're modeling homology. So we're connecting nodes that have common ancestors. So our edges in this case is ancestry and evolution, and our nodes are sequences or proteins. And we could also have different other biological networks, for instance, metabolic pathways. And in that case, for instance, we could model enzymes as nodes and metabolites as edges and how they interact in an organism to perform a given biochemical function. And the list goes on and on. So graphs are quite ubiquitous in biology. For instance, you can also model protein structures quite intuitively as graphs. So if you consider that proteins are a polymer of amino acids, and these amino acids, they form a polymeric chain that folds into a very specific 3D structure, which is very important for the protein to perform its function. And that's acquired due to interactions between the amino acids. So it's a very intuitive way to model, let's say, our nodes are residues, are amino acids, and the edges are interactions between them. And from there, we can then extract important information to represent that structure or predict its function, and so on and so forth. So just the general message here is graphs are everywhere, especially in biology, but in our day-to-day lives. So you can model a map, so cities connected by roads, and ask the questions how we best route between cities. We have connections, social networks, we can have physical networks, and computers connected by a network, and so on and so forth. There are different problems that are naturally modeled, so graphs are everywhere. And they are very important tools, mathematical tools, to describe and analyze these relationships. And if we could start then with a few basic concepts. So mathematically, a graph, as we've discussed before, is represented by a pair of vertices and edges. So we have two sets. V is a set of vertices that can also be called nodes, objects, items, and so on and so forth. And they are connected by a list of edges. And in that case, we can then introduce a new concept, which is a subgraph. So a subgraph would involve a subset of vertices from that original graph. So if you look on your right, so you have the original graph, so this big graph here. And if you consider only those 5 nodes here and all the edges that are within those 5 nodes, we can have a subgraph. So red would be a subgraph of the larger graph. And vertices and nodes, they could represent, for instance, physical objects, concepts, locations, and they can have labels. So it might make sense for you to say, this is a city, or this is a specific amino acid, this is a specific gene, while edges, they represent the relationships between them, between pairs of objects. They can also have labels, but also they can be directional. So for instance, when the relationships are different, you can label them and say this is stronger than this one, or it's a different relationship, or they can be directional. For instance, in metabolic pathways, when you have a reaction that it's not reversible, for instance, then you make a direction. When you have an ancestry relationship, you say this is a common ancestry from these sequences. You also have a direction applied to that. And also edges can have weights, so you can quantify the strength of the relation, for instance. And these combinations or these options or decisions you make while you're modeling your own graph, your own network, will define different graph types. So if we go on to a few different graph types, the first one will be undirected graphs. So if our edges don't have any direction, we would have an undirected graph, and we will consider the edges as an unordered pair of vertices. For instance, edge UV, it's an unordered pair. It doesn't matter if there is no direction from U to V or from V to U, and this could be quite important, for instance, and relevant for a problem, for instance, if you're modeling protein-protein interactions. If you're saying protein A interacts with protein B, and B interacts with protein A, there isn't an inherent direction there, so an adequate way to model it would be using an undirected graph, while directed graphs or digraphs, edges are also called arcs and are ordered pairs or vertices. So an edge or an arc UV is different from an edge VU, okay? And for instance, that would be relevant if you, for instance, are modeling a metabolic pathway, a part of a metabolic pathway. And for a given 2 vertices U and V, if they're connected, we say they are adjacent. Okay? And we can ask the question then, how many nodes are adjacent to a given node U? And that's another concept called node degree. So basically, I'm asking what's the size of the neighborhood of a given node. That's node degree. And node degree will vary depending on the type of graph you have. So if you have an undirected graph, the node degree is just the number of incident edges on that node. If you have a directed graph, you have two types of degrees. The in degree, edges arriving on that node, and out degree, edges leaving that node. Okay? And that could have implication in terms of finding specific structures and substructures in your graph. So basically, depending on the edge type, whether it's order or not, we'll have an undirected or a directed graph. And edges or nodes can also have costs or weights. And if we have a weighted edges, we will have a weighted graph. And that could be interesting, for instance, if you're modeling gene similarity or protein sequence similarity, something like that, that you need to quantify that relationship. While on unweighted graphs, you just have a binary relation. Either that relationship exists or not, and that, for instance, is relevant when you're considering homologous genes. If you recall from a few weeks ago, if we say to sequence a homologous, you don't say they're 80% homologous. They're either homologous or not. That's a binary relationship that implies common ancestry. While similarity, identity, that's a metric that can be quantified. You can say 80, 90, 100% identical or similar. Okay? So based on the biological data you have, you need to make a decision whether it makes sense or not to add weights to your edges. And another important concept is simple graphs will only have one edge between any two nodes, while multigraphs will allow multiple edges. So if we look at this graph here, and this graph here, the main difference is, let's say for this node to this node, we allow more than one connection. That would make sense, for instance, if you have two cities that are connected by different routes, by different roads, and they can be weighted, for instance, by their distance or quality, and so on and so forth. So we need to keep in mind how these decisions will affect then the algorithms as well. Another important concept is path and walk. So a walk is a connected sequence of edges. I know there's a lot of concepts, just bear with me, that you see how important they could be. Basically, a walk is a connected sequence of edges. So let's say we consider this graph here. We would say that a walk could be something starting from this edge or this vertex and going around it and up again. So this is basically a walk. So a sequence of adjacent vertices, while a path is a walk but without repeated nodes. That's the simple difference between them. And we can say that there is a cost related to the path, and this cost for weighted graphs will be the sum of all the costs of the edges in that graph. Okay? And with that, we can ask the question, for instance, how we measure and quantify indirect relationships. For instance, one thing is to say that these two nodes are directly connected, so they are directly interacting, or there are ways to interpret it. But you can, by identifying costs and paths within the graph, quantify indirect relationships as well. Asking the question, for instance, is there a path, is there a connection between these two nodes? And you can ask the question, what's the shortest path, or the path with minimum costs connecting two nodes in the graph? Okay? And there are different algorithms to do that. The most famous one is the Dijkstra algorithm, which is based on the breadth first search algorithm, which we'll see today. Okay? And that's quite important for routing and for the things as well. And a closed path will be then a cycle or a circuit in a graph. And so the first and the last nodes in a path are the same. If we do have a cycle in the path, we'll have a cyclic graph. If we don't, we will have an acyclic graph. Okay? So basically, a cycle is a path that starts and ends on the same one. So this is a cyclic graph because it has multiple cycles, and this is a cyclic graph. And why is this important? we do have a few special graphs. So we already mentioned a couple of them. This is a very famous one that traces back to the 18th century, which is the Eulerian path that Simon mentioned last week. And the Eulerian path, the goal there is to visit every edge exactly once. And for the brown graph, that's quite important because I'm trying to connect all contexts together. So I'm trying to find a Eulerian path in the brown graph, for instance. And as mentioned, this is quite important for de novo genome assembly. And this dates back actually to Leonhard Euler in 1736, which is probably the beginning of graph theory. And the problem that he tried to solve, and so many people before him tried to solve, the 7 bridges of Königsberg problem. Have anybody heard of this? Yeah. So it's a very famous problem. And the catch is the following. So there is Königsberg city here, and there is a river. And this river divides the city in 4 regions. So you have the north region, south region, we have an island here, and we have the region on the east here. Okay? And we have 7 bridges to cross. So if we go from one region to the city to the other, there are 7 bridges across this river. And the 7 bridge of Königsberg problem is, how do we define a walk through the city crossing each of the bridges once and only once? So if we model each of the 4 regions as a node, and the bridges connecting different regions as an edge, we will have this graph. So we have 4 nodes, which are the 4 regions, north, south, the island, and east. And we have 7 edges, which are the 7 bridges. And the question is, can we visit every edge exactly once? Can we? No? Why not? That's exactly what Euler proved with Euler theorem that states that we're not going to demonstrate it here. That states that in order for a graph to have an Eulerian path, that's difficult to say, Eulerian path, all node degrees need to be even. And it demonstrates it, okay? And what type of graph is this? So this graph is undirected, doesn't matter which way you go to the bridge. This is a simple graph. Nope, it's a multi-graph because you allow multiple edges between 2 pairs of nodes, and it's a non-weighted graph, okay? Did you ask something? No? And it's a non-weighted graph, okay? And we have a different type of path that was also mentioned, which is a Hamiltonian path or Hamiltonian cycle. And in this case, instead of visiting every edge, we want to visit every node exactly once. Finding a Eulerian path is a slightly simple problem. However, finding a Hamiltonian cycle, it's NP-complete. So there isn't a polynomial algorithm to solve it. Basically, in order to find a Hamiltonian cycle, you need to enumerate every single possible path in your graph, and that grows exponentially. And there's a very famous problem which modeling is basically finding a specific Hamiltonian path, which is the travel salesman problem, which is as follows. So you have a number of cities to visit. You're a travel salesman. You need to visit K cities. You want to go and visit every city only once and get back to the original city. And you want to do that as efficiently as possible, so driving as little as possible. So basically, the travel salesman's problem is finding the Hamiltonian cycle with minimum cost. So it's even more complicated than just finding a Hamiltonian cycle. And if a graph does have an Eulerian path, we call it a Eulerian graph. If a graph has a Hamiltonian path, we call it a Hamiltonian graph. And we do have other types of graphs that are quite important as well. The other type is a tree. So a tree is basically a connected, acyclic, undirected graph. Okay? And we do have different types of trees. A very important one is a binary tree, which will only allow for each node to have up to degree 3 if it's undirected. And we say that the tree is connected, or a given graph is connected, if there is a path between any nodes, any pairs of nodes, okay? And then we can ask the question, for instance, in trees, how many edges there is in a tree of size k, in a binary tree of size k. So let's say you have an algorithm, you have a list of nodes, and you keep connecting them to generate a tree, right? We talked about different algorithms to generate trees, for instance, using agglomerative clustering, and so on and so forth. In a binary tree, how many edges if I have k vertices? K minus 1. Why is that? Yeah. If you just think that you say you start with one node, right? And that's your tree with one node. And then you want to add another node. You add another node, you connect it. There's only one option. You need to connect it with your tree to just keep it with one connected component. Then to connect two, you need one. If you have another node, you need one more edge, and you can connect to both of them, to either of them, and so on and so forth. So every node you connect, you just need one edge. So you end up with n minus 1 edges. Out of how many possible? So if you consider a given undirected graph, we have how many possible edges? Can you say that again? Yeah? So number of nodes times nodes minus 1. One thing missing, divided by 2. So basically, the number of combinations, the number of pairs we have, n times n minus 1 divided by 2, which is quadratically, right? So it increases quadratically. So we can say that trees are very sparsely populated in terms of edges, okay? And on the other hand, we have graphs that are quite dense. And one of them are complete graphs or cliques. So cliques, on cliques, we have all possible edge between all nodes. And why are these important? They're basically important because finding small cliques in larger graphs would denote then finding, let's say, modules in PPI networks saying all these proteins interact with each other, maybe forming a larger oligomer complex that it could be important to function. So finding cliques in a graph is an important question to make. And then the number of edges in a clique is the total number of possible edges with n times n minus 1 divided by 2. So, but the next question is then, how do you represent these graphs in a computer? And the number of edges, of course, will then define what's the best approach to do that. And basically, we can divide this into different approaches. The first one is using an adjacency matrix. And in a adjacency matrix, the rows and the columns will correspond to the vertices. And let's say that a given element, aij, 1, 2, will receive a value depending on the type of graph you're modeling. Let's say aij equals 1, a12 equals 1 if there is an arc from 1 to 2. Or a given value if you have a cost associated with the arc. Okay? And also, we will explicitly denote when there are missing edges. For instance, if there isn't an edge, we'll leave it as 0. And this matrix will actually be symmetrical if we have an undirected graph, because we will then aim to connect ij and ji. Okay? The alternative is using a adjacency list, which is more adequate for sparse graphs. What's going to happen with this in memory? So as your graph grows, if you have really, really large graphs, the number of positions you need to represent your graph will grow quadratically in terms of the number of vertices you have, okay? And imagine you have 1 million nodes, 1 billion nodes. If you have 1 million, 10 to the 6, you have 10 to the 12 position in memory. So that grows quite quickly. So it's not a very efficient way to store a graph in memory, especially if you have just a few edges in there. Okay? So a more adequate way to store them in memory would be using adjacent list, would be something like this. So in that way, we don't represent missing edges. So each node neighborhood is represented then by a list. Let's say we say that node 1 has 2 and 4 in their neighborhood. And of course, this will have implications in terms of how do you access the edges and count node degree and so on and so forth. For instance, if we need to check whether node I and j are connected, if we have a matrix, we have a direct index in memory to access. So we just go R2 and 3 connected. We check automatically. We have an answer. While if we're doing adjacency matrix, we actually need to access the adjacency list of 2 and iterate through it. While this has a constant value in terms of processing costs, this, for a dense graph, could be up to linear. So if 2 is connected to every single node in your network, you need to repeat the operation up to n times. So it's less efficient to just check whether a couple nodes are connected or not. While calculating node degree, when you have an adjacency matrix, how would you do it? So I want to know how many how many nodes are in my vicinity. How do I do that with the adjacency matrix? I couldn't hear you, sir. You add 1. So you need to actually go through either a row or a column. And that's what's the cost of that. That's linear as well. You need to do that n times. While in a list, if you're clever in the way you implement your list, you always keep the number of items you have on it. So you have O1, so a constant cost. So you need to take that into account depending on how your graph looks like, whether it's better to implement it as a dense adjacency matrix or a adjacency list. And of course, that will impact memory usage as well. So, and you can also store graphs in a file, either representing them as a whole adjacency matrix that will cost a lot of space, or using, for instance, an edge list. So just labeling all the edges. So let's say there's an edge between 1 and 2, 1 and 4, so on and so forth. And you just store in your file that edge list. And adding to that, then you can add another column with the cost or the label. This is a more efficient way to represent it. And now we're going to talk a little bit about graph traversals and how we visit nodes in a graph in a systematic way. And graph traversals, they are very important algorithms. And the main difference between them are basically the order in which the vertices are visited. And a specialization of graph traversals are tree traversals that we already talked about a little bit as well. And on tree traversals, we'll aim to visit each node only once. And the two main algorithms for a graph traversal are depth first search, DFS, and it's quite useful for us the question, is there a path between two vertices U and V? Are they connected in some way? So the main idea on DFS, on depth first search, will be traverse deep into the structure, visiting children nodes before we visit the neighborhood. So if you look at this graph, we'll try to go deep into the structure first before visiting the neighbors. While, and for trees, depending on the order we decide to visit the nodes, we can have 3 types of algorithms: pre-order, in-order, and post-order. And we'll look at them in detail in a bit. And the alternative is breadth first search, BFS, which will give us the answer for the question, what's the shortest path between two nodes U and V? And the idea here, on the other hand, is instead of traversing deep, we'll traverse broad into the structure, visiting the neighbors first, and then we visit the children nodes. So DFS. The main procedure for DFS is easily implemented recursively. So this does look like a tree, but it isn't a tree. So because it's a cyclic graph here, okay? even though we're going to talk a little bit about traversing trees as well. So basically, the procedure for deep first search will receive as input a graph and a given vertex. Let's say we start with A. And it will go as follows. So it's a recursive procedure, since I'm calling DFS here. And we'll then label the first node as discovered or visited. And for each node W that it's in V's neighborhoods, so each of the adjacent nodes to V, if it hasn't been discovered yet, I will call the function recursively. So the effect of this is basically, I'm going to go to A, which is my first node, the first function call, and then basically I'm going to discover it, and for each of the neighborhoods, I'm going to call DFS again. And the effect of this is basically, when I get to B, I'm going to call DFS again until I can no longer go deep into the structure, and then I return visiting it, okay? And that's the implementation using recursion. Alternatively, we can implement deep first search using a very useful data structure called a stack. If you remember what a stack is, if you think you can arrange elements in a list, the stack will basically be a list where you add elements to the top and you also remove elements from the top, okay? So the first element added is on the bottom, will be the last one to leave. So last included is the first out. Last in, first out. That's a stack, okay? So basically for the iterative DFS, you're also going to receive a graph G and a given vertex. And for that, you're going to need a stack, let's call it S. And first thing you do, you include V in the stack. You push it, you put it on top of the stack. And until S is not empty, what we're going to do is we're going to remove an item, check if it's not discovered or visited. If it is visited, we'll not visited, we'll visit it. And then we'll add each of the nodes of its vicinity, adjacency, to the stack and continue the process. So the order of nodes visited in this case will be the following. So we'll first call, let's say we're starting from A, we'll visit A, we'll visit A, then we'll visit B, then D. Once we can no longer go, we'll backtrack from B. B has already been visited, and continue from F. Visit F, then continue deep in the structure to E. A has already been visited. We can no longer go. We backtrack from F, from B, from A again. So the only branch that hasn't been visited is this one. So we go from C and then G, and then we stop. Okay, we'll go in detail in a little bit with a different example. So in terms of tie complexity, eventually you might need to check every single edge of your graph. So time complexity, or DFS, is O of E, where E is the number of edges in your graph. Okay? And the iterative version will need a data structure called a stack. So looking at an example of the first search, the analogy for the algorithm is basically solving a maze. How would you go about to solve a maze? Let's say you have a big maze, you have an entry, and you have an exit. And the entry and exit analogy could be you asking the questions, is there any path between the entry and the exit? Okay? And you can do that with the first search. Does anyone have any idea of how to actually solve a maze? Not related to graph theory, just solving a maze. You're having a real scale maze. How would you solve it? There's a very simple ways to solve it. You can keep going on always left, or alternative, which is the same thing. You go on the entries, you put your hand on one of the walls, and keep going. You follow the walls. And that will guarantee you always find the exit. It could take a while, but you will always find the exit. So it's a systematically way to check every single option. And basically, that's the main idea of deep first search. So you're going to walk through the maze until you reach a dead end. When you do, and you will, you go back, you backtrack until you find an alternative route that you haven't walked yet. So it's like you're in the maze and you have little bits of paper. The way you go, traversing the maze, you leave paper, don't litter. That's just an analogy. And once you reach a dead end, you just go back the way you go. until you find, let's say, a bifurcation, and you try again in a different direction until you find the end. And then you repeat this process until you find your exit, hopefully, or die in the maze. And so let's consider this graph here. What type of graph is this? This is a simple graph. I can't see multiple edges between nodes. It looks like it's a directed graph. So there is directions here. I can go from A to B. I can't go from B to A. And deep first search is valid for all sorts of graphs. Not necessarily this one. This is just an example. And we can start from a arbitrary nodes. Let's start from A here. So in this case, we have 7 nodes. Let's start with A and see how we follow. So for this case, then, we will need to keep track of our stack, okay? And the first thing to do is we'll start with A. We will add A to the stack, okay? Second thing we do is we're going to visit neighbors of A. And then we'll visit next C and add it to the stack, okay? And from C, we ask the questions, can we continue moving on? And from C, we can go to D. Notice that from A, we had 3 options. We could go B, C, or G. The order in this case doesn't matter, okay? So first we go to, let's say we go to C. We stack C. Then from C, there is only one option, which is going to D. And we add D to the stack. And from there, from D, the only way to move forward is actually going to E. We put E to the stack. And from E, we reach the dead end. We can no longer go anywhere. So what we do is we remove E from the stack and mark E as visited. So E now is marked as visited, and my stack looks like this. So we have A, C, and D. So we need to backtrack. So we reach that end, we return to D. What's the other option for D? Would be then going to F. We add F to the queue, to the stack, sorry. Next then, what we could do then is from F going to G. And from G, we could go to C. However, C has already been visited, so we reached another dead end. And from that, we need to backtrack and find another alternative. So E has been visited. The next one to be visited is G, which will be removed from the stack, F, D, and C. So in order, they will be visited as E, G, F, D, and C. And then we'll end up with just A in the queue. And from A, we still can go to B. So B is added to the queue. And from there, we already visited every single node in the graph. And then we have our deep first search. We mark B as visited and A as visited. And then we visit every single one of them, okay? This could be valid for all sorts of graphs, not necessarily directional. So when we have trees, however, we will have 3 different options in general in a way to do a deep first search in a tree. For this case, let's consider just binary trees. In binary trees, we'll have 3 traversals, deep traversals: pre-order, post-order, and in-order. And that will affect the order the nodes are visited. So pre-order, basically, we're going to do is we're going to visit the current nodes. Let's say we start with the root, always for the tree. We're going to visit the nodes. We are going to visit in depth the left subtrees, then the right subtrees. And this is basically a recursive call. For post-order, we will actually leave the visiting stage to last, and then we will recursively follow the left subtree in pre-order, then the right subtree, and then we visit the node. While in order, we will traverse the left subtree, we will visit the node, and then traverse the right. Okay? And while this just seemed like alternatives, each problem might require different ways to traverse this tree. So what are the order of nodes visited in pre-order? Let's say I ask this in the exam, give you a tree like this, and just a pseudocode like this. So what's the order? that nodes are visited in pre-order. So what's the first one? So let's say we start with the root, which is F. First one is F. I visit F. Next thing I do, what do? I traverse left. I traverse left, and I visit left. B. I keep traversing left. A. I can no longer go. What do? I backtrack to B. B has already been visited. Then I already visit. I can't go left. I go right. D. I visit D. Next thing I do, left, and I visit C. Can't no longer go, backtrack to D, then E, and so on and so forth. So F, B, A, D, C, E, G, I, H. Is that correct? Yeah. What about post order? Post order, I will try to go left until I can't anymore. So we reach this point, we can no longer go forward. So I tried left, can't go. I tried right, can't go. Visit A, go back. Do I visit B? No, because I can still go right. I go right before I visit. Go right, then I go left, can't go. Visit C, backtrack. Still can go right, visit, can no longer go visit, can no longer go visit. So it's A, C, E, D, B. And then we do the same on the other side, which would be H, then we go back to I, then we go back to G, then we go back to F. And the root is the last one. And what about in order? Which is the first one? A as well. So in order will be the following. I first try left until I can't anymore. I can't. I visit. I go back. Once I have exhausted the left range, I visit. Then B. Then go right. Then go left. Can't go anymore. Visit. I've already go back on the backtrack. I can't go any further on the left. Then I visit. Then go E. And this will return. Once I reach to this point, backtracking from B to F, this left would have been exhausted, so I visit F. Then I go to G, which is basically pre-order on right. I can't go any further on left. I visit G. I go I can still go left. I go to H, visit H, go back, visit I. Okay? Alternatively to depth first search, we can do breadth first search. So the main procedure and the main difference for breadth first search is instead of a stack, so this is not a recursive, so it's an iterative algorithm. So instead of using a stack, we're going to use a queue. What's the difference between a stack and a queue? Sorry? Yes. So basically, on the queue, you add on the end of the queue, you remove from the start of the queue. While in the stack, you insert and remove from the same end. Okay? So what's going to happen on breadth first search will be, well, we need a data structure, which is a queue. Let's call it queue. And we'll also receive a graph and a given vertex to start with. This is an example with a tree, but it's valid for every type of graph. Let's say we start with F again. And what's going to happen is let's enqueue or add the vertex to the queue. Let's visit it. And while the queue is not empty, we'll remove one from the queue for each node's W in its agency. If it hasn't been visited, we'll add it to the queue. We'll keep track of its parent just to know where we've been, and we visit it. So the effect breadth first search will have is basically on each step. So let's say starting from the root, so each step I will visit every nodes that are one edge away from the nodes, then 2 edges away, then 3 edges away, and so on and so forth. So for instance, we start with F, then we will visit nodes that are 1 edge distance, B and G, then the others that are 2 edges away, A, D, and I, then the others that are 3 edges away, C, E, and H. And that it's because of the way we use the queue. And that's the order of the nodes visited. In terms of time complexity, it's the same complexity as depth first search. Worst case scenario, we will need to check every single edge, and it needs a queue instead of stack. And this is often used to find shortest path from one vertex to another. And the idea behind this is every step we're assessing all nodes that are from a given distance. So if we have an unweighted graph, the shortest path between 2 nodes will be how many edges in the path, okay? All the edges are the same. Let's say all the edges are weight 1. So there isn't a difference between them. It's an unweighted graph. So shortest path between any 2 nodes will be how many edges we have in the shortest path, okay? And breadth first search will give that to us. And we'll also end up producing a breadth first tree, which will define shortest path from our node V to every single other one in the graph. And just to have an example for breadth first search, let's say we start with this graph here. And let's start with a random node. Let's call it B. And let's assign it to level 0. Okay? What type of graph is this? This is a simple graph. I can't see multiple edges. It's undirected. What else? It's unweighted. Is it acyclic? No, it's cyclic. There are many cycles in there. Okay? So let's say we start with B, and we keep track of our queue here. First thing we do, we add B to the queue. Next, we visit B. So we visit every node that is at 0 distance or level 0 from a starting node. Next thing we need to do is add to the queue. So we remove B to the queue, and we add all the neighbors or all vertices that are within 1 distance from B. In this case, A and F, we add them to the queue, okay? Since they haven't been visited yet. And the next thing we do, we'll need to visit each one of them. So let's say we visit F. F has been visited and marked as visited. And then the next thing we need to do is take a look at F's agency and to see if there are any nodes that haven't been visited there. There is G and C, and we add G and C to the queue. Next up, we remove the next element, which is A, which is the last element on level 1. So these 2 are 1 edge away from 0. And we check its vicinity. We only have E here, and we add E to the queue. Next up, we'll be visiting C, which is the next element to the queue, checking its agency to see whether there are nodes that haven't been visited before. There is G and D, but G is already in the queue, so we just add D. Our next element to be assessed is G. G is removed from the queue. We mark it as visited, and then we add the last item to be assessed, which is H. And then we queue will have just E, D, and H left. And then we visit E, remove E from the queue. We visit D, remove D from the queue. There's nothing else to add. We visit H, remove H from the queue. And we have our breadth first search iteration finished. Important and very interesting thing about breadth first search, however, is the following. If we keep track of what we've done on this graph, what we will end up and is with all that parent node thing, which basically is this instruction here. So keeping track of where I've been on the graph, this will lead us to a tree. starting from B and reaching all nodes. And this is, for instance, a breadth first tree, and we'll define the shortest path from B to every other node in the graph. And that's one of the ways for an unweighted graph, you get shortest paths from one node to every single other node. Okay? And that's it for today. What we're going to do then next week is how we're going to use shortest path calculations, degree calculations, and so on and so forth to better extract information and understand different types of networks. So we'll talk about complex networks and network analysis. And that's it for today. Thank you. Hi.
How to verify like if my tree creation is correct or not? Is there a way that I can verify? So we are using three distance matrices, and the tree is different for each of those.
It will be, yeah.
Is there a way to verify like because I don't know if my logic of the branch distance is correct.
For instance, you can get different examples. Different examples that you have. This is an input. This is how you do it. And you can use it externally. Of course, you wouldn't submit it in the end, but you can use externally. I would use externally. So this is how it should look like. And I input it to the algorithm and see that they can recover it.
Or like is there a way to use scikit bio without the neighboring join check like
Better not. But there are different ways to do it. There are other libraries to do it. To check, yeah, definitely. If you Google it, you can find other libraries. If the purpose is just checking the reference is corrected, I can't point to the right direction.
No,
That's different to it. But yeah, you definitely can. And that's something interesting. So when you produce code, you want to make sure it's correct, right? So we've given you just a couple entries, but you don't have the entry. Right. So if you could find then examples with the entry, with the input and the output, fine.
okay. And the thing is like I'm really struggling with interpreting the results. So so the last one I was trying to make an argument with the phylogenetic tree. So like my intuition is that the naming convention so like KLF should be goes in the tree. And like one of the distance metrics is doing good. But for example,
The problem is the following. Who told you? Well, it makes sense for KLF 1 and 3 and 7 be close to each other. It makes sense biologically because you're inferring from the name that they are homologous.
Yeah.
That's one thing. That doesn't mean that the algorithm using those parameters will see them.
yeah,
You know, it's a different thing. It might not be wrong. The tree might not be wrong. It's just not a good tree.
yeah,
You know what I mean?
yeah, because that's
Just
what
on
you are
previous
asking,
meetings to judge
Yeah.
the results.
and that's what you are asking, like which one you think is.
Yeah, and then you can argue that these are real sequences, because then you can make an argument. This makes sense because they're related, explain their function. But you understand that the differences between the algorithms just that they don't manage to encompass and represent the actual evolution.
Just quick questions. Can we import it like the other library, like copy? Because I need to use maybe
That depends on the library.
so is it
Which one?
the copy
Copy.
one?
What does copy does in that case?
Just wanted to make it copy because if you just use the equal to make those two equals and if you change one values of this one, because this just a point and then the other values of the other dictionary also.
Okay, what I don't mind, but would you mind asking how many? Because when she's gonna mark,
She needs to make sure that's installed and available.
I think the copy one is the default.
If it's a default, I think. Which one? Which library?
The copy one. Because I want to use the deep copy.
I think it should be by default.
Yeah,
but
I
you
think-
can run. If it runs, that's fine.
I don't know what.
Because that's the server.
Okay, yeah.
That's the server, right?
Yeah, that's just.
So I think if that
If
is
it's in the
working,
server,
Should be on. That should
and if that's not